Okay, good morning. I'm sorry that I changed the title of my speech. Actually, while sitting that corner, I'm still thinking about my the title. Maybe it should not be the historical perspective. Maybe it should be ecosystem perspective of XPU. Maybe it's more appropriate. So let's first explain what's XPU. Actually, we have CPU and a microprocessor. Actually, CPU exists when we have a computer in 1940s, but microprocessor only appears in 1970 when large-scale integration becomes real work. And at this time, at current time, all the CPU chips are actually system on a chip, including the CPU cores, memory controller, peripheral controller, and lots of stuff on a single chip with the help of ultra large-scale integration. Traditionally, we classify microprocessor as two kinds. One is general purpose, meaning the processor is used in computers with higher performance, running complex operating systems. Also, we have another kind that is embedded processor, maybe called MCU. But now, the classification of these two kinds are getting closer and closer, not so clear. Because, for example, some devices previously we don't think it's a computer. For example, the telephone, we don't think it's a computer, but now we have smartphone, it's just a computer. Also, for those cars, we don't think it's a computer, but now it becomes a new, maybe become a new computing platform. So it's a processor inside the car maybe become a general purpose processor. And also the artificial intelligence recently drives the new demand for computing power. And many startups in both in United States and in China, we see many startups design different kind of microprocessors or other accelerators. So we have besides CPU, we have GPU, we have TPU, we have NPU, we have DPU. So I call all these kind of PU XPU to meaning all these kind of processors. So we also use a new word to computility processor, which means those processors providing big computing power. So this is the outline of my talk. Actually, the subtitles may more. It will be more appropriate if it's expressed in Chinese. The first subtitle, separate long, close surely, close long, divide surely. In Chinese is 三国定律啊，分久必合，合久必分。So I will talk about the instruction set. Generally, we have different kind of instruction sets. Now convergence to one or two. This is a kind of three kingdom law. The second one, I will talk about the economic base determines superstructure, which means 经济基础决定上层建筑. This kind of consolidation, the reason for this kind of consolidation, not technical, it's just economical, I think. The third one, subtitle, is spiral development of processor industry, which means 计算机芯片产业的螺旋式发展。Actually, we have different. Previously, we have computer system vendors designing chips, and the second stage, all the chips are provided by independent chip vendors. Now, all the system vendors, many system vendors, platform vendors are also designing chips now. So this is a spiral development. So let's go a little bit about the previous times. We have the computing system or the computing model. We have also different kind of evolution. First from mainframe, centralized mainframe, to distributed client-server system, and then now to the cloud computing, which is combination of centralized data center and ubiquitous different kind of clients. And also, after we have microprocessor, the computing platform, we have different kind of computing platform. In the past, we have a personal computer, which leads to things is not used only in the office. It's as an office device. It's also popular of all the computing every time in entertainment for the PC. And the second platform is smartphone. Smartphone is everywhere in our daily life due to its mobility. So that now we are seeing the appearance of the third kind of computing platform. It's autonomous vehicles. So for this kind of products, actually the dependable security is much important. Now also we see three mainstream CPU architecture or instruction set architecture in three kind of platforms. For PC, we have x86. For smartphone, we have ARM. And for autonomous vehicles, we don't know. Maybe, is this a chance for the RISC-V? I don't know. I hope to, but I don't know what will be in the future. So I'll talk about the separate long, close, surely in instruction set architecture. Actually, ISA is the interface between hardware and the software. There are many different instruction sets in the past, and mostly I say we don't know it already. We only see them in the text box of a computer. So, for example, Intel has its own RISC processors, iXCT, i9CT, yeah. But now they don't have that. Intel also developed the EPIC style IA64 with HP, but now it's also out of line. And Motorola have its own Cisco microprocessors, and also they have RISC processor, PowerPC, and HP, PA RISC, SunSpark, Digital Alpha, and SGI MIPS. They all, most of them have gone. Yeah. Now x86 dominates the desktop, and the ARM dominates the mobile. So what's the reason for such kind of convergence? And is it a necessary or actually accidental? According to my idea, let's also have a look of typical those instruction sets. In 1960s, IBM System 360 proposed the concept of instruction set architecture, and in the 1970s, actually different kind of instruction set architectures appears in the world, and actually this decade is a test field of different instruction sets. We have simple load store architectures, also very complex CISC architectures, like VAX 11, and also there are some efforts in designing high-level language machine. Also, x86 appears in this time. In 1980s, we have the battle between CISC and the RISC. Which one is better? So since we have VLSI, we can integrate a whole CPU in a single chip. In 1990s, we have the most popular is superscalar RISC processors. We have Alpha, MIPS, PowerPC, and others. So, but in the new century, all those RISCs gone, and we have x86 and get there. It's perfect success in the world. Actually, x86 is not just a CISC. It's an integration or fusion of CISC technology and the RISC technology. I think this graph is from IDC, but it's several years ago, the data. At that time, we see in critical business sectors, RISC EPIC servers are less and less. And the four-way x86 servers are replacing them. And also, the four-way x86 servers were replaced by the two-way x86 servers. So why this kind of phenomena? Actually, how the x86 win the battle with RISC? I think x86 is much elder than RISC. In 1980 or 1990, x86 has advantages in PC area and the risks in workstation and the server area. But we can conclude two reasons for x86 success. Technically, x86 are continuously improvement and in its implementation technology. It learns from high-end RISC processors and using deep pipeline to get fast clock frequency and also adapting dynamic out-of-order execution to greatly improve its performance. And also, x86 continually enhance its characteristics by introducing new instruction subsets according to the requirement of new applications. And another aspect, economically, the x86 has the advantage of mass shipment, which means its cost is more competitive. In x86, we know both Intel and AMD designs PC and server CPUs using same CPU core microarchitecture, which greatly amortizing the development cost of server CPUs. So RISC fails for, I think, also two factors actually limit. We have two factors limiting the development of high-end CPU or other kind of processors. The first one is the existing software and hardware ecosystem. So ecosystem is very important. So I mentioned before that I should use the title ecosystem perspectives of XPU for this talk. And there are different kinds of standard or de facto standards such as instruction set architecture, which is very important in the ecosystem. And also the cost for developing a new processor increase year by year. That we have non-engineering fees for all the new chip design increase especially with the semiconductor node comes to advanced one, and the line size becomes language becomes smaller and smaller. So and also this is what we think about this kind of situation. It's actually a technical issue or it's an economical issue. Actually, I think it's not just a technology issue. It's more important, it's an economical issue. Since developing new hardware, new software, both involves big cost. And compared with new hardware, even redesigned the software is much more expensive. So I will talk about it later. We'll first look at the cost for hardware design. The cost for advanced processes and advanced chip development. In the previous days, when we have 32, 28 nanometer technologies to build a semiconductor factory of 32 or 28 nanometer, we need more than $1 billion US. But if we go to 20 nanometers, additional $3 billion US need to be invested to have the new factory. And for 14 nanometer and below process, the money is much more. We need maybe 1 billion, 10 billion or more to build such a factory. And also, the design of cost for high-end IC chips is also increasing rapidly. In 32 nanometer node, usually a project needs about 50 to 90 million US dollars, but after 20 nanometer, maybe in 14 or 7 nanometer process, the typical development cost is $200 million. And now for 5 nanometer or 3 nanometer, it increased much bigger. So how a chip product covers its development cost and get profit? There are two solutions. One is sell in big volume. Another one is sell in high price so that we have high margin. In the textbooks, we may think we still can see all those literatures we see. In 1990s, we have many startups designing supercomputers. There are vendors designing massively parallel processor based supercomputers using the company's own processors. For example, we have N-Cube, we have Thinking Machine, we have Kendall Square Research, we have MassPro, we have MECO, and this kind of supercomputer startups. So that's actually, in 1990s, it's a very good decades for architectural innovation, different ideas. For example, the KSR proposed a comma architecture named all-cache. It actually implements the first comma means cache-only memory architecture. In the whole system has only cache, no main memory. But the project is not so success because its own designed CPU runs at only 20 megahertz, while at that time the commercial products from Intel have 486 has already reached the 50 nanoseconds. So actually we have many architectural innovation in that decade, but they failed in front of the economic scale, or actually they are defeated by the economic rule. Not just technology is not good. Also, I will talk about the second issue. The economic base determines the superstructure. The 经济基础决定上层建筑。Actually, the architecture, the word architecture, if we translate it into Chinese, it's generally 建筑. But actually, we also in computer area in Chinese we say this 体系结构. It's actually 体系结构建筑 are the same word. So from technical perspective, actually we see x86 the instruction set has many weaknesses. For example, it uses variable length instructions. Instructions length maybe 1 byte, maybe more than 10 bytes. So it's difficult to prefetch the instruction and decode the instruction. It uses very few registers, and some registers has its own special usage. So it's difficult for compiler to generate efficient code. Also, it's used flag registers recording carry, zero, parity, and other states. And the branch of x86 depends on conditional code, which will be revised by previous instructions, but we don't know which instruction may modify the conditional code. So actually, the x86 is traditionally, it's very difficult to get a high performance implementation. But Intel, AMD, they have a secret, which is microcode. Using the ancient, actually, microprogramming technology helps the x86 greatly, which also alleviate x86 drawbacks in high-performance implementation. This is a diagram of a typical x86 processor microarchitecture. In the middle of this architecture is the macro instruction layer, 72-bit RISC-like macro instruction. Actually, the macro instruction set is a RISC, actually is like the RISC machine. So the front end of the processor translates the complex x86 instruction into strings of macro instructions, which also, well, we call it a microcode. And the back end of the processor is just an out-of-order execution RISC machine. So gives the modern x86 very high performance, just like a RISC machine. So at this time, we have a different kind of architectures. All the instruction set architecture, actually, for the architecture, is partitions the work. Which work should do by hardware, which work should we do in software. So we have different kind of I classify three kinds of macro architecture. The first one is aggressive architecture, which use dynamic optimization runtime dynamic optimization as soon as possible. So such as the comma architecture I mentioned before. And the aggressive architecture assumes that the software has its limitation in dynamic analysis and optimization. Also, this kind of aggressive architecture tends to a very complex hardware, and also the hardware consumes much more power. Another one, in the opposite, is conservative architecture. It's only use static optimization. For example, the hardware provides facilities to get high performance, but how to use, such as the registers with SRAM on the chip, but how to use these facilities to achieve high performance depends on software. So in conservative architecture, we have simple hardware, but it's maybe hard to program or hard to program the architecture to get performance. So performance have no definite guarantee. Most of the architecture we see is the compromised one, which use hardware-software co-optimization. Hardware do some dynamic optimization, such as we provide a cache. Cache is a dynamic optimization mechanism. And also, although hardware do some optimization, dynamic optimization, software still has its space to do more optimization. For example, software program or compiler can reorganize the data access patterns so that the cache miss rate may be lower. So this kind of hardware-software collaboration is we can get more performance, and the programmability tends to be better. So generally, all the CPU products are aggressive ones, especially for the server CPUs. They need to support complex operating systems, compilers, and other control-like applications. So all these applications have many serial parts. So parallelism is difficult to express or difficult to exploit. So use hardware to exploit those parallelisms. So in this kind of aggressive architecture, hardware dynamically analyze instruction series at runtime. So we have issue with maybe wider issue weights and very bigger and bigger instruction windows, and also the bigger reorder buffer sizes. So different. So all the we have commonly we see more than 100 and more than 200 instructions are issued but not committed. So to realize these, we have outer order execution, we have branch prediction, we have speculation, we have hyperscalar execution. So also multi-level caches are used, and level 1, level 2, level 3. And now we also have a concept of system level cache. And for x86, we also have the cache for microcode. And also the simultaneous multi-threading are used in this kind of processors. This kind of aggressive processor have too complex structure. Since it's too complex, it's very difficult to verify the correctness of the design. So how the project commonly it will be delayed, and the time to market is much longer. And also, I think starting in 2019, that this kind of aggressive architecture have its own weakness or exposed. They are exposed to transient execution attacks, such as, so we see the hardware defects such as Spectre and Meltdown. It's just due to the speculative execution. So talk about aggressive architecture. I need to talk about the China indigenous processor development. We have in China, we have maybe we have our foreign friends maybe not so familiar with China's own microprocessor. Actually, we have many years' work in this area. At least, I think, starting from the year of 2000. What we can see today is that actually great progress have achieved in the past 2 decades. The China based microprocessor, the performance we can comparable to those mid-range Intel AMD products in the market. And also, we have several million shipments annually of China-based microprocessors. And we have successful commercial deployment of China-based microprocessors in telecom operators, in banks, in power grid, and those actually mission-critical application areas. But for China-based microprocessor, the industry and the technology ecosystem is still weak, especially in supporting those software, in the supporting software and application softwares. Also, we have some weak in too much options for the end user. We have multiple instruction set architecture, ISA options, and multiple operating system options in the China market. So these kind of options diverses the R&D research and the development cost of the whole society. For example, in instruction set, China based processors, we have 2 vendors working on x86 instruction set, 2 working on ARM-based instruction set, and we also have long arc, which is previously is MIPS. We have SW64 architecture, which is previously is Alpha, and also we now have many RISC-V vendors. So much kind of processor architectures. And also for the operating system, also, although all based on Linux, we have different kind of distributions. For example, we have Qilin, we have UOS, we have NFS China is a founder. UOS is Tongxing. And also we have now Harmony is Hongmeng, and or many others. So the combination of processor architecture times the operating system is much more. We have actually we have a very complex situation for the mix of different ISA, different chips, CPU chips, and different operating systems. Actually, currently I'm working on a GPU startup. We are designing GPUs to support those China-based systems. So we are facing a very complex ecosystem. We need to optimize or adapt our product to our GPU cards to I think many configurations. The number of configurations is the number of number of the microprocessors times the number of operating systems. So actually we are facing the more than 30 different kind of configurations of the computer. Also, we see during the past several years, we see that for the microprocessor design, the China and the US, we have actually some technical gaps between China and the US. And in research side, we can see that the two countries have similar or almost the same research capabilities. For example, we have, for China, scholars have publications in all the international journals and the top journals and the conferences. And also, we have several national key laboratories continue their frontier area research in computer architecture, in circuit, in the testing, in compiler, OS, etc. But actually, I see that there are still a big gap remains in engineering, in the design and implementation side. For example, the performance of China indigenous microprocessors is lag behind the leading edge US products. And also, our application performance is much worse since our software ecosystem is not so good. This kind of gap cannot be closed only by we strengthen our basic research. We need more effort in engineering. Actually, I have seen different directions in the research and engineering. Actually starting from 2000 in the new century, the performance improving of a single core processor is no longer a hot topic in the research area. So if you look at the ISCA papers, then we see less and less papers, or few and few papers are discussing those microarchitecture, single core microarchitecture. The topics of research paper transfers to many core and other architectures. But improving single core performance is still an effort of most engineers in company engineers. For example, these two figures I drawn from the spec CPU data for Intel processors. actually in the 10 years, we see in the 10 years, the Intel single core processor, Intel Core, the performance still have big increase. For example, integer performance increased 4 times, and the floating point performance increased 7 times. So this kind of the source of the performance improvement origins from modification of microarchitecture. Since the clock frequency in the previous about 20 years is really same, not so big change. So why the engineers still working on the single core improvement? Even we have multi-core, we have many core, but single core performance, there are still strives to promote. There are several reasons. I think the first one is for many core or multi-core, we need parallelize a serial program to let the program to be useful for the many core processors. Some applications are easy to parallel, but some others may not be easy to be parallelized. When in parallel works in parallel form, efficiency will be lost for a few tenths. And also for all the legacy applications, those applications without source code, the parallelization is very difficult or even impossible. Another important issue is that many enterprise-level mission-critical applications, for example, database, for example, ERP, for example, EDA tools. I'm working in a fabless CPU design company, so we need to buy EDA tools to design our processors. Then all these mission-critical applications, we buy license. We buy license. All those license, how many license I needed is counted on the number of processor cores used. Each core, one license can deploy. So if the single core, the performance of each core is lower, then the user needs to buy more licenses to fulfill its computation requirement. So software license is much expensive than the hardware. So single core performance needs still to be better and better. So why such kind of microarchitecture modification doesn't occur in university or research institute, only occurs in the company? Because this kind of work generally is not so innovation. In principle and the methodology is the same. So same the multi-layer cache, same multiple issues, same out-of-order execution, and others. And so if working on this kind of work, no paper can be published. So, and also this kind of work requires stable, precise, and predictable performance models and methods and tools. We needed measurement analysis based on large amount of real workloads. These, and also we needed RTO level fast prototyping equipment. All those is time consuming and expensive. So for university and enterprise, we have different kind of performance evaluation principle criteria. So only this kind of work can be did in corporation, not in the institute. After talking about the aggressive architecture, we now move to another different kind of accelerators, which generally use conservative architecture. Since Moore's law, although becoming slower and slower, but we still have more and more transistors can be used. So how to improve performance by accumulating all those transistors. A simple idea is parallelism. We have wider data bits, more functional units, and more processor cores. So this is, we have all these facilities, hardware facilities on a single chip, how to manage and control them. So we need, this comes to different kinds of conservative XPUs. Most of computing applications often have natural parallelism, and such as image processing, molecular dynamics, and neural network for artificial intelligence. So in those XPUs, hardware provides sufficient ALUs, memories, interconnects, and software express the parallelism, control the execution. So parallel programming, there are two kinds of tasks. One is use parallel programming based on parallel language and a parallel compiler. Another one is using parallelizing compiler to transfer serial program to parallel one. So we have different kind of XPUs. For example, we have dedicated designed accelerator such as Intel Xeon Phi, Google TPU, and others. And also there are accidentally appeared accelerator. This is, I use this accidentally, means generally GPU is only for graphic rendering, but now it can be used for general purpose computing. So GPU comes to GPGPU. But for those high-end, especially XPUs, ecosystem will be a big issue. Since what is ecosystem? I think ecosystem is a total software running on the processor, including application software, system software, and middleware, and other supporting software such as different kinds of libraries, application-oriented. So for CPU ecosystem, x86, we have two ecosystems for CPU, x86 for computer area and ARM for embedded area. But now we have RISC-V only works at present time, works in embedded applications with simpler software stack. And maybe in the new computing platform, the software is not so mature. So but in embedded area, the RISC-V ecosystem is still far behind ARM in system software and the development environment. Also, the ecosystem is much worse, is a big issue for those conservative XPUs, since they have conservative design, relies on software to improve performance. But at this time, only CUDA dominates this area. And in China, we have many XPU vendors. And I think US, there are more, but they are also limited by the CUDA environment. All the users like CUDA, not other guys, the processor. So talking about the ecosystem, x86 is a very typical one. Actually, after more than 50 years evolution, x86 occupies more than 95% of the computer market, formed a very strong ecosystem. And also, starting from 1994, Intel and HP jointly developed IA64 CPU, which is using EPIC architecture, but is not x86 compatible. This effort consumes, I think, billions US dollars, but it actually, 2 decades effort, 2 decades effort, but still the product stopped shipment in 3 years ago. So we see that even Intel is not able to design a non-x86 CPU successfully. So how about other companies? So as we see in the foreseeable future, x86 will still dominate PC and server market. This is an example of x86 ecosystem. I asked my colleague in Hygon to get this data. it's from Gartner Enterprise Software Market. So it's several years ago data. We have statistics here. x86 revenue share in enterprise market, and also this line is revenue coming from x86, the software revenue. Also the R&D investment in software for x86 architecture. So each year, the revenue, software revenue is more than about 400 billion, and the investment in 2018 is about 60 billion investment in software. We have a reference from IDC, the global server market selling hardware. The revenue is only 8 billion, but the whole system invests on the software development for x86 is near 60 billion. So the whole ecosystem invests much more than hardware to enlarge this x86 ecosystem. So what's the chance for ARM 64? In the past decade, we see more than 1 decade, we see many companies working on ARM CPU, but falls and rise, many one. In China, we still have many vendors doing ARM-based CPUs. The motivation for non-x86 CPU is clear, since the industry doesn't like x86 dominates the market. Just like now we have many AI chip makers want to share the NVIDIA's cake, want to see NVIDIA's dominance. But it's also very difficult for ARM to success, since just I mentioned, the x86 ecosystem is very strong. So ARM CPU success, there are some cases, for example, system vendors with their full stack technology don't like using x86. Maybe it can use ARM. For example, Apple is an example. Apple, all the software stack is controlled by Apple itself, so the ecosystem migration is possible. And also there are maybe some fusion of cloud and the terminal side. For example, the cloud side can take advantage of ARM's advantage in mobile, such as, for example, Android cloud. So ARM servers can run Android applications directly, no emulation needed. Cloud gaming is another kind of case. So how about the RISC-V? It's open source one. So actually, RISC-V is not the first open source instruction set. Previously, we have OpenRISC, OpenSpark, and even OpenPower. And RISC-V allows the designer to modify instruction set, which will lead to the divergence of the RISC-V ecosystem. And there are some reasons talking about RISC-V is important. The one is that ARM is too expensive, so RISC-V gives users more chances. But I don't think ARM is too expensive, especially in previous several years. We see 5 years ago, ARM's annual revenue is only $1 billion, not so big. And the whole mobile application processor market is 20 billion, more than. So ARM collects, the money ARM collected is not so big. But recent years, ARM is a little bit expensive. ARM's annual revenue reaches 3 billion. And also, ARM's this improvement is under the competition of RISC-V. So this is a kind of interesting situation. RISC-V, also there are some saying that RISC-V is more appropriate for research, since we can modify it and others. But I think if not for commercial purpose, only for research, we can use XDX and modify it. We can use ARM and modify it. We have we have many open source. Actually, in my area, we have open sourced architecture emulators such as Zhimin and others. We can use different kind of instruction sets for research purpose. This is okay. And also, open source is not an advantage for microprocessor. I think we think open instruction set or open hardware is much more difficult to success compared with open source software, because even we have the free code of the microprocessor, we'll still need large money of big NRE to get these code to be fabricated, to become a chip, become hardware. So it's not like open source software. We got the Linux code, we hit the return key, compile, then we have the operating system binary. This is easy. But for hardware, it's not so easy. So we see global difficulty in RISC-V, the commercialization of RISC-V, because new instruction set lacks software support in its infancy time. And recent success of RISC-V all in the embedded fields with simple software. We mentioned it before. For example, MCU for storage controller, such as Seagate and West Digital are using RISC-V. And the RISC-V still needs time to enter computer or mobile phone area. And also, we see many IoT-related cases. They have, their IoT applications have divergent or fragmented requirements. Each application have different kind of requirement. So RISC-V have this advantage that modify the ISA and have spatial extensions to meet those special requirements of the IoT applications. But this kind of modification means that we need to design many MCU or many SoC for different kind of purpose, which leads to the divergence of the product. And so the product may be much expensive since the shipment is small. Also, RISC-V's hardware ecosystem is not so mature. For example, we don't have competitive, like ARM competitive commercial RISC-V cores and high performance network on chip, which high performance interconnect to supporting multi-core integration. Many RISC-V vendors are still using ARM-based interconnect IP to design a multi-core one. Now ARM doesn't allow this kind of usage. For ARM knows you are designing RISC-V processors, so ARM will not sell its interconnection IP to you. So actually RISC-V community needs its own high performance NOC. So there are another point of view talking about instruction set, saying that maybe in the future, instruction set are not so important. Actually, several years ago, I have this kind of idea, but now I don't think so. There are several reasons for this kind of thoughts. For example, software-defined anything. Well, they are talking software-defined everything. And also, we have emulation. We have virtualization. We have binary translation. We can emulate one instruction set with another. And also, there are many kind of cross-platform languages, such as Java, such as Python, and related tools. This simplifies the migration of the applications in different platforms. But we have I observed recent years many upside effects. For example, Intel continually extends its x86 instruction set with a different kind of instruction subsets, such as SGX for security, AVX for vector processing, and AI extension for supporting emerging AI applications, which this kind of work means that direct support of hardware instruction is very important and essential to higher performance, to lower cost, to lower power. So direct instruction support is very important. Also, I see, it's, at least in China, that public clouds only use Intel CPU, not others. I met with Ali Cloud. For public cloud, they only use Intel, even not AMD. So China-based, they don't use in the public cloud because they need to frequently support all kinds of old OS versions and old configurations, old OS. All these Intel supports very well. Others support not good. So all the system and application software, no matter open source or commercial software, are mainly optimized for Intel CPU, even not for AMD CPU. Although two vendors have similar ISA, similar x86 ISA. So there are still many vendors are designing domain-specific architecture, DSA chips. We see that DSA has already written into famous computer architecture textbooks. So this means it's actually important. And many startups developing DSA accelerator chips, especially for AI purpose, for DPU, they are designing domain-specific architecture. But on the other hand, we see that Intel didn't make success in its Xeon Phi accelerator. The only Xeon Phi, biggest shipment of Xeon Phi is to NUTD in China, the Tianhe supercomputer. But when NUTD Guofang Keda is on the entity list, Intel fails in selling its Xeon Phi processor, then this kind of product fails also. And we also see a fact that NVIDIA doesn't allow its desktop GPU to be used for mining Bitcoins. Why? Because NVIDIA's desktop GPU and server GPU are similar, same microarchitecture. But desktop GPU is sold in much lower price. If desktop GPU can be used for mining, then server GPU cannot be sold to customers. So need to be some distinct. Which means I use this example to say that domain-specific architecture is domain-specific, so will be small shipment, only small shipment. Those small shipment products are not economically survivable. Even high margin cannot cover its development cost. So NVIDIA GPU, NVIDIA used desktop GPU to cover its R&D cost. And the high-end server GPU, actually, it's the same one, can be sold in very high margin. So it's NVIDIA's successful strategy. Other vendors, if you just use a domain-specific idea to get that high volume, it's very difficult. It's not easy. So, the last topic, I hope I consume too much time. The last topic, spiral development of processor industry. Actually, previously, we see system vendors design CPU, since CPU is essentially the key of computer system. So in VLSI time, we have IBM, HP, Dell, Digital, not Dell, design its own CPUs. And afterwards, all these guys left, and we have Intel, AMD, NVIDIA, independent processor vendors. Now we see system and platform vendors starts developing its own processors. In the United States, we have Apple, we have Google, we have Amazon, we have Microsoft designing its own CPU or other PUs. In China, all the big internet giants, BAT. And the second tier internet giants, the TMD, or design its own. BAT designs CPU chips by themselves, and the TMD want to design or support other guys designing processors. And also we can see Huawei, Lenovo, Xiaomi, even Oppo are designing their processors. So this is the market to see market data for all those server shipment, x86 server shipment. Actually, it's similar to all the server shipment data. So we see investment for designing a CPU. This is my experience. If we have good technical team and experiences, we as a follower, 我们叫跟跑哈，我as a follower, our product, if the product is one generation behind the leading edge Intel AMD product, then I know we need 4 billion RMB investment and 2,000 engineers work about the average 10 years experience. It's possible. If we need, our aim is same stage with the worldwide leader, then the annual investment need to be about maybe 10 billion RMB and more than 3,000 engineers work. The difference between the follower and the leader is that the leader need multiple project teams work in parallel in case one project fails. And also, the leader need to try exploring all newest devices, newest fab processes, newest packaging testing technologies. So they need time and money to try the errors. For the follower, always do the right decision, since all the leaders are tried the errors already. So this is case for a China-based CPU vendor. If the processor, the product's average sales price is 4,000 and the gross margin is 50, then to gain 10 billion RMB gross profit should sell 5 million units. 5 million units should be sold. This means you occupy all the China market. Generally, it's not possible. So to obtain 4 billion gross profit, you only need to sell 2 million units, then means occupying 40% of the China market. This is also very difficult. We see in the this graph gives the occupation actually of those vendors. So 40% is very difficult to achieve. So we need actually for CPU vendors in China need other solutions to keep its sustainable development. For example, sell in higher price, higher price, and also financing in the first and secondary market to get the money. Also, you need to get wider market, for example, desktop market and worldwide market. So internet cloud service providers design its own chip is a trend, became a trend we all see. Actually, this kind of work is their developed chips for its internal usage is feasible since their profit obtained is by the service they provided, not hardware sold. So relatively easy to cover the cost of the chip R&D cost. But since they have fully control, all those internet service providers, they have fully control to the hardware software stack. So less difficult for them to migrate its software to the new platform. So let's revisiting the successor under those not so successor. Phase one in design, those vendors design its own processor. We see Apple is obviously successful in designing its own CPU. Previously, Apple used PowerPC. After 2006, they tend to use Intel CPU. Now, several years ago, they are using its own based ARM CPU. Why ARM can success in designing its own CPU? The appearance is a sense. 现象就是本质. ARM, the appearance is that ARM is too expensive. Our product is too expensive. This is why it can win. So ARM designs its own core. Not ARM, Apple designed its own CPU core. Then they only have architectural license from ARM. They do not use ARM's ARM-provided core. So Apple's core is higher performance. We see Android phone have 8 cores in the chip, but ARM only have 2 cores, but the performance is much higher. Adapted with its own software achieves optimal user interface, and also with marketing help to appear, ARM appears a very high-end product, so with very higher price. So it's successful. Design its own CPU and make success. Others in China, we have when we see some companies is also designing its own CPU, but I think maybe you know the company Oppo. Oppo have started a big team in designing CPUs, but they fails to until close the project 1 year ago or 2 years ago. Why? Because they only see the appearance, design own chip, but design just for use is useless. Design CPU need a value add with your new product. So in summary, for the platform or system vendors, differentiation is very important for designing own CPU or other chips. And the more important is that this kind of differentiation will be used, need to be used to generate add-on value to the system or service you provided. And for those independent chip vendors, need to understand the importance of software ecosystem. Software defined everything. This is a slogan, software defines anything. I think even software defines success. So for hardware guys, need to know software. And for instruction set, actually, it's just a language. Proposing a new instruction set doesn't mean innovation. More instruction sets, then more additional work in the software ecosystem. This is no good. So maybe we unify language. This kind of instruction is very hard, but we shouldn't add more languages or more instruction sets. And architectural innovation, I think, can happen in the framework of existing instructions. The worst case is we add some new instructions or subsets in the existing ISA is enough. Finally, I have 2 appeals. The first one appeal the international giants such as Intel, AMD, NVIDIA open their private interface. For example, grant a free license to x86, free license to ARM architecture, and GPU instruction set for NVIDIA. Thus, then, if this kind of free license is granted, then the whole world will leverage the software ecosystem thereon. This is a big benefit to the whole society, whole world. I think this first appeal is very difficult to achieve, so I have the second one. In case this first one not work, then we have the second one. The second one, all other CPU, GPU, and XPU vendors, except those giants, Intel, AMD, NVIDIA, adhere or migrate to RISC-V instruction set to share a common ecosystem, so that we can eliminate those duplicated development efforts in different ISA. Actually, not CPU, or only those XPU don't have. We see TPUs and DPUs, NPUs, too many different PUs, different architecture, consumes whole society too much effort. So if we can unify in the RISC-V, then the whole society also can spend less, and we can get the final, our aim to build a low carbon society. Yeah. Thank you. Any questions?
Let's give our great thanks to Professor Zhimin Tang for his speech on the development of processor. Because of the time limitation, we have only one question. Is there any question? Okay.
Hello, Professor Tang. First of all, thanks very much for your insightful talk. My name is Bin Cao. I'm from Zhejiang University of Technology, China. Though I'm not working on the field that you talked about, I'm really wondering, what's the next step that China needs to take in developing chips? Thanks.
This is a good question, and difficult to answer. Actually, in China, I think we have too many chip vendors already, CPU and other, GPU and DPU and others, too many. More than the total of the other world, I think, especially more than United States. Even we see in the United States, we have many big, except those Intel, AMD, those giants, we have also startups in doing new kind of processors, but the vendors and the startups in China is much more. So this is actually not a good phenomenon, I think. We need to consolidate. Maybe I think China government is working on this, working on the consolidation of operating system vendors in previous years. For example, we maybe 6 or more years ago, we have made about more than 10 operating system vendors, Linux vendors in China. Now they consolidated, most of them are consolidated to the GOS. This is, I think, it's a good effort for those CPU vendors. Since CPU vendors are much stronger, since designing CPU means spending more money, so they are much stronger than operating system vendors. So actually, relatively difficult to combine them, to integrate them. For example, they have background. Different vendors have different background. For example, background of Chinese Academy Sciences, background of the military side, background of industry work side, MIIT. So they have different kind of background, so difficult to merge. But I think that all these companies they have inventors in the back, in their back. So the financing system need to to do more work. And also I see the government is encouraging this kind of merge of the chip vendors so that all those small processor vendors can combine to maybe less than 5 vendors. Then all the efforts of the and the resources of the China society can be more concentrated on this area. So maybe everybody can get enough market for its own survival. Yeah, thank you.
Thank you again, Professor Zhimin Tang. It's the end of the keynote. Thank you all.